Hi everyone. In the previous lecture, we spoke in great detail about the RC non-inverting RC differentiator. So to complete that discussion, in this lecture we will talk about the non-inverting RL differentiator. The circuit shown here is a non-inverting RL differentiator. So if you want to find, we can easily find the transfer function for the circuit by using the result 1 plus Z2 by Z1. Z2 is the impedance in the feedback path. Z1 is the impedance at the non-inverting terminal. So if you use that, you will get 1 plus SL by R, which is SL by R, which can be written as 1 plus S tau. So if you look at this expression, it's not a pure non-inverting differentiator. It also comes with a proportional term. Okay, your output signal V naught of t is given by V. This is the transfer function written in Laplacian domain. In time domain, the output voltage will be given by Vi of t plus tau dVi by dt. This will be the expression for the output voltage. Okay, so this part contains the differentiator information. So this part is the proportional path. It just has a proportional component which is just like a voltage follower. So it follows the input voltage and also performs this differentiation. So first, to analyze this circuit for a step input, we will follow the same approach as we did for the RC differentiator circuit. Okay, so first we will find out the boundary conditions and then try to find the reasoning as to how the circuit reaches these boundary conditions. So first, when the step input arrives, at t equal to 0, suddenly the inductor will act like an open circuit. Assuming the inductor's initial current is 0, the current through an inductor cannot change instantaneously. Okay, the circuit will not be able to change the current through the inductor instantaneously. So I can assume it to be an open circuit. Okay, so saying it is an open circuit is equivalent to saying that the current through an inductor cannot change instantaneously, or the incremental impedance of the inductance will be infinity, right? So this impedance, step input signal at t equal to 0 can be seen as a sinusoid of infinite frequency. And the impedance of your inductance is what? The magnitude of the impedance is omega times L. So it blows up to infinity. So that's why I've written it as open here. So inductor will act like an open circuit. So there is no path for the current through the resistor. So the resistor voltage will be 0. The input non-inverting terminal is at delta V volts. So the total differential input at the op-amp's input is delta V volts. So assuming since it's a positive step voltage, delta V is greater than 0, your output will be at plus Vsat. So at t equal to 0 plus, it suddenly your output jumps to plus Vsat volts. In the steady state, your inductor current would have reached a final value, and the inductor will now act like a short circuit. So that's what I've shown here. The circuit will reduce to something like this. We have a DC input of delta V volts, and the inductor is acting like a short circuit carrying a constant DC current. So this circuit, assuming delta V is fixed, delta V is a step input, so the input of this op-amp will be fixed at delta V volts. So now this circuit looks like a voltage follower. So output voltage will directly follow the input voltage. And the node voltage Vx will also come to delta V volts. So the circuit starts off at plus Vsat and then eventually reaches delta V volts. How does it reach that? We'll do the analysis in this lecture. So first, before we actually analyze this circuit, first we need to find out the initial conditions. How does this circuit behave at 0 minus, at t equal to 0 minus? So since it's a step input, the input's value at t equal to 0 minus is 0, right? Step arrives only at t equal to 0, it jumps to delta V volts. Before that it is 0 volts. So we are going to assume that this RL differentiator circuit has reached a steady state even before the step input is applied. Okay, so because it has reached a steady state, we can treat the inductor to be like a short circuit. If the inductor is like a short circuit, then the circuit reduces to a voltage follower, and the output voltage will simply follow the input voltage, which is 0. So output voltage comes to 0. And this node voltage Vx also is at 0 because the inductor is like a short circuit. So V naught of 0 minus and Vx of 0 minus both are at 0 volts. Okay, so maybe if I forgot to mention, Vx is the node voltage here for this circuit. We will try to find out both the output node voltage and the inverting node voltage, right? Both these node voltages contain all the information that you need to know about the circuit. So now when the step arrives, suddenly when a step of delta V volts is applied to this op-amp's input, we already saw that the inductor's current cannot change instantaneously, so it will act like an open circuit, and this node will go to 0 volts because the no current through the resistor, so this node will be at 0 volts. A huge step input of value delta V appears at the op-amp's non-inverting terminal, so the differential input to the op-amp is delta V volts, so the output will suddenly jump to plus Vsat. When the output jumps to plus Vsat, the op-amp now is in the saturation regime. Okay, the saturation regime where the incremental gain of the op-amp is 0. If the incremental gain of the op-amp is 0, then the incremental loop gain is also 0. So even if your node voltage Vx changes by small amount, the op-amp is not going to respond to that. So I might as well remove the op-amp and treat the op-amp like a voltage source of value Vsat at the output port. Okay, so that's what I've shown here. So this is your op-amp's output V0 connected to an inductor, and the output node, the inverting node voltage is Vx. Now once the output reaches Vsat volts, the node Vx, the inverting terminal node voltage, will start increasing, and it will undergo a first order RL charging. It's a first order circuit, so it will undergo a first order charging. So it will start off from 0 and slowly increase to reach plus Vsat. Okay. Now as this node voltage Vx increases, the differential input to the op-amp decreases. Okay. And when your Vx reaches delta V, the differential input to the op-amp becomes 0. Now you reach the high gain point. When you reach the high gain point for the op-amp, output voltage can change now. It can change suddenly. Okay. So what happens is, at this point when the differential input becomes 0, that is when the inverting terminal reaches delta V volts, the output voltage will now start decreasing. Why will it start decreasing? Because this node voltage Vx has a tendency, it has a tendency to increase. It's just not stopping at delta V, it's increasing. Because it's increasing, the output will have a tendency to decrease. So it will start from plus Vsat and then slowly keep decreasing until it reaches plus delta V. When it reaches plus delta V, the voltage across the inductor becomes 0. Okay, because Vx has reached delta V, the inductor voltage will become 0. The output node voltage has also reached delta V. Okay, so Vx took a long time to reach delta V because it was a first order charging. But the output node voltage took no time. It suddenly jumped because op-amp is now in action, right? Op-amp's output, when you are in the high gain region, it can change suddenly. So it suddenly, from Vsat, it jumped to delta V. The voltage across the inductor is now 0 and the current through the inductor will remain constant. Okay, it will not change anymore. If the current through the inductor remains constant, this node voltage across the resistor will also remain constant. That will also stay put at delta V. At this point, none of the node voltages or currents in the circuit is changing anymore. So then we say the circuit has reached a steady state. Okay, and the time at which the circuit reaches steady state can be found by equating the time at which the node voltage Vx of t reaches delta V. And that voltage, we have already derived this in the previous case, will turn out to be equal to tau ln of Vsat upon Vsat minus delta V, as shown in this expression. Okay, so what happens to the circuit? At the output voltage for this non-inverting RL differentiator, the output jumps to plus Vsat at t equal to 0 plus, starts off at 0, jumps to plus Vsat, and then after t on seconds it suddenly jumps back to delta V volts and stays constant. And I can use the same logic and say this output makes sense. This output reaching eventually delta V is mainly because of the proportional term. The transfer function of the differentiator is 1 plus S tau. So this one term tells us that the output voltage will follow the input voltage in the steady state. Okay, this term S tau is the transient term, and this pulse that you see, sudden jump to V side and then following back to delta V volts, is the differentiator's response to the step input. Okay, this guy, the output remaining at constant, is the response of the proportional path. Okay, so that's the behavior of an RL circuit. I mean, I just explained here that the circuit reaches steady state when the output directly jumps from VSAT to delta V. You can also assume the op-amp will reach the high gain mode and start assuming that the op-amp's gain is finite, and also derive and show that mathematically you can argue that it will reach, the steady state operating point that the output will reach will be when the output reaches delta V volts. It starts at VSAT and it reaches delta V volts. Okay, so that's it about the performance of the step response of a non-inverting RL differentiator.